morning, George. Good
Hi.
morning, Bern. Yeah, how are you? Yeah.
Good, thanks. Yep.
Yeah, thank you so much for agreeing to give this talk. I mean, it's been some quite a bit of an event over the past week.
I can imagine, yeah.
Yeah.
Texas, the energy country or the energy
Well,
state, right?
Yeah, yeah. I mean, yeah. Apparently, you know, the Texas power is completely independent.
Yeah,
so
I know.
Texas don't want to have anything to do with anybody else. that didn't go very well, you know.
It's strange that they allow you to have this meeting,
well,
which is international.
Hey, Bern, how are you?
Hi.
Yeah.
Hi, Bern.
Nice to see you again after a long time.
Yeah. Thank you so much for agreeing to give this talk. Yeah. So there's no snow. I see your background. There's no snow in the I guess you're in FW. I mean, that's East Germany, right? That used to be
East Germany.
Yeah,
but
right.
There's a couple of days we have something like 20 degrees centigrade, so it's really nice weather.
Oh, 20 degrees centigrade.
Unusual,
Okay,
but it's let's say a little bit different than in Texas, I think.
Well, no, today is good. Today we're going to be reaching 70s. Last week was bad. Last week was like 18 degrees Fahrenheit. Yeah.
Fahrenheit, yeah.
Yeah. So
that's cold for Texas.
No, that's very, very cold. That's very. But George, you're American, right? I mean.
I'm Canadian, yeah.
You're Canadian? I see. I see. Okay, I see.
Yeah, originally from Manitoba, where it's -40 nowadays.
I see.
Centigrade, but there the scales cross actually at about -40.
Okay, so minus so 18 degrees Fahrenheit is nothing for you, right?
No, that's balmy weather. You go in shorts.
18 degrees, you go in shorts. I see. Yeah.
Well, in Vancouver, it's much milder. So
I see. Yeah.
It froze last night, just barely, but we've had almost no snow. Yeah.
So Vancouver is very similar to Seattle, right? I suppose because
it's quite rainy in the winter time.
Yeah.
Hi, George.
Hi there. How are you doing?
Hi, thank you.
Good to see you.
I also saw Tomo here. Tomo, hey, Tomo, how are you?
Tomo is there.
Yeah. So Tomo and I are organizing the Frontier Condensed Matter Physics seminars, you know. So yeah, that has a lot of good talks as well. Yeah. But this Zoom thing, you know, I mean, can be good and bad, right? Zoom, you know, it's very convenient. But bad is that there's very little personal interaction. You know, you don't get dinner. You know, chat. You don't have a private chat and things like that. You know, nothing. Yeah.
Don't hear the real story, huh?
No. But the attendance typically is very good for these things. Yeah. So we typically.
Oh, that's great.
Yeah, we typically have like you know, easily 50, 60 people.
Yeah. Oh, that's pretty good. Yeah.
Online for these. Yeah. I thought Qimiao wants to say. Qimiao is going to be here soon. Hopefully, you want to say something.
Morning. Hello, Christian.
Hey, Qimiao, you want to say something? Like 1 minute?
No, I'm good.
You're good? Okay. So we're going to talk about pneumatic phase today. Yeah. So Bernd is going to talk about pneumatic phase in 1111, and George is going to talk about pneumatic phase or something close to pneumatic phase in iron selenide.
I don't think so.
Morning, Josh.
That's not what I thought.
Okay, whatever.
Whatever.
We still have a minute to go.
Yeah, I know. Yeah. No, so you're actually in your office. I mean, yeah, you'll be more diligent than I am. You know,
I love my office at this time.
Yeah, hopefully another 2 months things will become normal, right? Yeah.
Yeah, where are the vaccines?
Yeah,
Actually,
let's wait one more.
Yeah.
Let's wait 1 more minute. Yeah.
Georgia, what's the situation with the vaccines in Canada?
Well, we're a little bit behind, actually, as far as the number of vaccinations per population, shall we say.
Mm-hmm.
So we're at only 2% or something right now.
Okay.
But it's supposed to be picking up soon. And Canada's had a lot of trouble because Canada doesn't have any. They have trouble with Pfizer because Pfizer, of course, we're getting the vaccines from Belgium, from the factory in Belgium, because the U.S. doesn't want to deliver to other countries, right? But we are getting some now, and Pfizer is picking up. Yeah, so it'll be okay.
Oh, so there's no factory in Canada?
They actually closed it about 10 years ago. Well, less than 10 years ago, 8 years ago or so. Yeah, with the Conservative government, we now have a Liberal government, so they opened it up again, but it'll take a while before it's operating. It's really disastrous to not have any facilities like that. Yeah, we have research in vaccines.
Yeah.
As a matter of fact, there's a vaccine coming up, which probably seems to be working very well from Canada, but we don't have a manufacturing place.
So George, does Liberal government means higher inflation? And that's what a lot of conservatives are saying.
Well, that's what they always say. But once the Conservatives in, you find out that the inflation is higher there than it is now. The inflation is inflation has been very low, actually.
I see.
So we've had a Liberal government now for what, 6-7 years, 6 years, I guess. 6 years.
Okay, so there's no correlation.
Yeah. And I don't think that there's really any correlation. Yeah.
So Chima, can we get started?
Yeah, please. Yeah, please.
Yeah. Okay. So I mean, yeah, very good. Yeah. So we're very pleased to have both Bernd and George to give a talk today. So Bernd will talk about the lanthanum 1111. I guess the string effect, right? Basically the pneumatic phase. And yeah, okay. So he's a director of IFW in Dresden. Okay, yeah, please. It's all yours.
So hello everybody. So first of all, I would thank the organizers for inviting me to give this presentation. I would like to bring you back to the early days of these iron-based superconductors by showing you some of our recent work on these 1111 type superconductors. Let me just show you an outline. So first, I would like to convince you that these systems are really extraordinary iron-based superconductors. And then I will show you some progress in crystal growth. And that's, I think, the main motivation for us also to pick up this story again. We're discussing pneumatic fluctuations in these systems. And then if I have time enough, I will also discuss some more recent work on strain-dependent measurements of Seebeck effect and Nernst effect, and which gives some additional information on the pneumatic instability and the connection to electronic structure of these systems. Let me first mention the people involved in this work, and the main person first was Rea Kappenberger. Maybe I first have to. She was the lady who managed to grow the nice crystals, or which I will show you later on. NMR and NQR measurements were done in Hayo and Piotr Lepucki mainly, and then the transport was done by Federico Caglieres and Xiaocheng Hong. And then I will also show you some thermodynamics done mainly by Federico Scaravacci. Good or bad metals? Well, let's take this as a starting point. So I think most of these iron-based superconductors, if you just look at the resistivity, behave like rather good metals. So this is an example from our own work. This is lithium iron arsenide, which has a small residual resistance, more or less T squared at low temperatures. and a large resistance ratio. But there is one exception, and this exception is indeed these 1111 type superconductors. And this, the first report on superconductivity in these materials, and there you already see that you're basically dealing with something which is very close to localization, very close to insulating behavior. And the smallest resistivity which I found so far was one which was measured in a small single crystal here. And you still see, if you look at the absolute values, this is far away from being a nice metal. And you see here this typical phase transitions. You see above the phase transition, there's this increase, this tendency to localization. But the main message which you can take here from such a figure is that there is a strong decrease of the resistivity when you do this entering. And this immediately tells you that the scattering, which determines this very high value of the resistivity at high temperatures, that this scattering is intrinsic. It's not extrinsic, or not only, mainly intrinsic. So you have a very strong intrinsic scattering, which is dominating the electronic transport, leading to the fact that these systems are very close to localization. And that's also what you see as a function of doping. This very early data where you see that when you leave this magnetic phase, you still have in the so-called underdoped region, still have this tendency to localization. Only if you go to very high doping concentrations, you end up with a resistivity which qualitatively looks like that, what we know from these very nice metallic systems. Okay, and this is, I think, is important because at the end of the day, these systems, these 1111 type systems showing the highest TC in the bulk iron-based superconductors, they are 50 or 60 Kelvin TC. So factor of 2 larger than that what you observe in all these metallic systems. Therefore, I think it's interesting to have a closer look on the materials, have a closer look what is determining really these very strange, unusual normal state properties which we have in these materials. Let me highlight another point. What's also quite characteristic for these 1111 type systems is something which people call poisoning effect of superconductivity. So you start from an optimally doped lanthanum 1111 type system, you plug in 0.2%, that's basically nothing, of manganese, and you destroy superconductivity. And it's not only superconductivity which you destroy, you can have a closer look on these publications. It's a normal state which drastically reacts on tiny amounts of disorder. Again, telling you that these systems are far away from being easy, simple, good metals. And this figure is also important because later on I will show you cobalt-doped compounds, and this tells you already that this doping has a strong impact on the properties of these systems. Okay, so that's background. So the big step which we made in crystal growth was done a couple of years ago. It's a very unusual procedure, so-called solid state crystal growth procedure, which allows to grow pretty nice, well-faceted single crystals, three-dimensional single crystals. So that was first done on 1111 type crystals, so on the parent compound of these compounds, and it's still ongoing procedure. It's a very complicated process, and we still are not completely happy, and we are still improving this thing. But this shows the potential that you can really do single crystal studies, and which gives much more insight in the properties of these systems. Let's have a close look on the phase diagram, which is known also since more than 10 years, an old work by us. We have revisited this also for powder samples. What is known is that we have a very strong suppression of the magnetic ordering or the structure phase transition. And this is also seen in the more recent data. Now, meanwhile, we managed to get a smaller Tn down to 30 Kelvin. So it's not this first order-like behavior, at least not for the magnetism. There we can follow it down to lower temperatures. But there is still a clear separation between magnetic order and the structural phase transition. And so the pneumatic phase transition and magnetic ones are well separated. And what we still have is there is no coexistence between superconductivity and magnetism. So you have this well-separated region, and you end up with a region of so-called underdoped compounds where TC increases similar like we know it from some of the cuprates. So that's very similar to the first thing. We also managed to get, let's say, an internal standard. So the main problem is just to measure the electronic doping, and this you can do via NMR. And if you want to know more on that, you can have a look on this paper where we describe that. And you can even take all the literature data, put it on the same phase diagram, and then all the things fit together. So that's the phase diagram which we know for these compounds.
Bernd, do you mind if I interrupt you for a second?
No.
Maybe you'll talk about it, but near the doping where the magnetic order goes to 0, say when the T nail is about 20 Kelvin or so.
Yeah.
Is there something unusual about the resistivity versus temperature, for example?
I cannot tell you about that. It's still, no, it looks like this close to localization behavior.
Okay, thank you.
I cannot tell you, in these cobalt doped compounds, which I discuss later on, this intrinsic scattering due to cobalt is so strong that I will not discuss that, but I will come back to that later.
Okay, thank you.
Okay. So that's the phase diagram we are dealing with for the fluorine doped compounds. So what we managed to do so far is crystals of a series of cobalt doped lanthanum oxygen, so lanthanum 1111. So cobalt doping means electron doping. This we know from the other systems, but it means also impurities. And I've shown you the figure of this manganese doping. That also means that we are not expecting the best crystals. We do not expect the best superconductors because we have intrinsically impurities in there, and they play a crucial role. But that's okay. That's a challenge for crystal growth, and the thing what we managed. And here we can do it up to rather high concentrations. We can really control the stoichiometry. Therefore, that was the first series of samples which we studied. And then we measured the phase diagram, and we did a broad spectrum of techniques to study that. And this is, let's say, a highest resolution measurement of the structure. So the dilatometry, where you see the temperature derivative of the lattice constants, you see the structural phase transition or the pneumatic phase transition here, and then you see the magnetic phase transition, even there, even the lattice constant, you can see that as a function of doping, the transition shifts to lower temperatures, as we know, and everything becomes very broad. So in particular, this structure phase transition becomes very broad if you start to dope it. And you can also see that from the lattice constants, which you can derive from such kind of measurements by measuring twinned and detwinned directions. And then you see this sharp transition becomes broader and shifts to lower temperatures before it disappears. You can also, of course, measure the magnetization just to follow the phase diagrams. So for the parent compounds, you clearly see these two phase transitions. And if you start to dope, the structure becomes very broad again. Surprisingly, the magnetic transition becomes sharper, very nice visible. Some probably telling us something, but it at least gives you the chance to measure the phase diagram. If you go to higher doping, systems become reasonably good superconductors. Optimally doping, TC is small, but this is known because cobalt reduces TC, cobalt impurities reduces TC. But it's also clear that you see magnetism disappears at about 4.5%. Superconductivity is very strong with 6%, and in between we have, let's say, very weak superconductivity and no magnetic order. So we used also NMR to study the properties, and that confirms the things which you get from the macroscopic properties. So you see this very strong change of 1 over T1 when the magnetic order is still present, and then it disappears and we lose the long range order. We can also, looking at the satellites, we can also determine there the structure phase. So at the end of the day, we end up with the following phase diagram, which shows again the splitting between pneumatic and magnetic phase transitions, shows decrease. We lose the signatures of the structural phase transition, pneumatic phase transitions at about 4%. We can follow the magnetism down to these concentrations, and then superconductivity emerge. So that's qualitatively very similar to this phase diagram. Maybe it's a little bit broadened here in this region, but of course we are now discussing compositions in the second digit of the cobalt. So that's the situation. So that's the phase diagram, and it's somehow similar to that what we know for the fluorine doping with a suppressed TC due to cobalt impurities. So now let's start. We have now single crystals at hand. Let's start to do more experiments. And the first thing what we can do It's well established, meanwhile, is this pneumatic susceptibility measurements. So what we measure here is the strain derivative of the resistivity. So we piezo, we have crystals glued on top of that. We measure the strain, we measure the change of the resistivity, plot it as a function. So plot resistivity as a function of strain, take the derivative, we get the pneumatic susceptibility. This shows this divergence close to the structural phase transition. That's all well established for the other systems. Here you can see that this fit is not so bad. This Curie-Weiss fit is not so bad. And you can extract the Curie-Weiss temperature, which is close to whatever, 130 Kelvin for the parent compound. And this you can do now for all these doping concentrations. So this Curie-Weiss fit is more or less working also for doped crystals. What you see then is that this Curie-Weiss temperature becomes smaller. And then you can follow this behavior up to very high concentrations. So this is now underdoped, and we go to overdoped samples. And when you just look at the Curie-Weiss temperatures, you see that it first is positive and it crosses zero just to optimal doping. So this is the best superconductor which we have in these systems. And then it becomes negative for the overdoped compound. So it's very easy to see, easy to identify the optimal doping here from the normal state strain derivative of the resistivity. So this is the corresponding diagram of this pneumatic susceptibility, so this characteristic temperature, this Curie-Weiss temperature as a function of doping. You see the crossing here at 6%, it's just there where we have optimal doping. So in some sense, you continue this line here, though the structure phase transition or the real 3D order disappears. Just looking at the characteristic energy scale, we follow this line and it hits exactly the zero for optimal doping. Or you can also, yeah.
I'm sorry, can I ask a question?
Yeah,
right,
sure.
So in the parent phase, you observe T pneumatic about 20 or 30 Kelvin below the actual transition, right?
Yeah.
But it looks like from this phase diagram that they actually are about the same temperature when they reaches the quantum critical point. No?
That's right. That's correct. Yeah, I can. So you see, here's 130 degrees is TM. The structural phase transition is 150 degrees. So, but if you go to this TNM at higher doping, it enters the zero.
Okay, so in some sense, the separation temperature gets smaller and smaller as you're approaching
the separation temperature between, let's say, the ordering temperature and this TNM becomes smaller. And then, of course, I've shown you the data. This transition becomes extremely broad. And therefore, I don't know what that means. Yeah. But we can
Thank you.
Not only look at the pneumatic transition temperature, we can also look at these, let's say, susceptibility. So what I've plotted here is just the absolute value of this strain derivative. And you just look at the data. It's raw data. Nothing is done with that. So it's the optimal doping. So we have a pretty large number here. So there's a very strong change of the resistivity as a function of a strain. If you go to overdoping, it becomes much smaller. And if you go to underdoping, it also becomes much smaller. It also becomes smaller when you go to the parent compounds or to these strongly overdoped compounds. So without any manipulation of data, you just take the raw data and plot that as a function of doping, you end up with this diagram. And then you see this, what I would call a double dome feature here for this pneumatic susceptibility. And it's easy. So one, of course, this is, let's say, mimicking our superconducting dome. There's nothing, just taking the resistivity, the strain derivative of the resistivity, we directly can see the region where superconductivity occurs with a maximum at least 6%. And the other thing here, which we see here, is also a special point in the phase diagram, is exactly the phase diagram, close to the region where magnetism disappears. And it's, of course, let's say, natural to assume that here this is the coupling between pneumatic fluctuations and spin susceptibility, which we see there. And that there is a coupling, we know, of course. We know, for example, from measurements of NMR, when you go to the magnetic phase, to the pneumatic phase transition, you see a strong enhancement of 1/T1T, so strong slowing down of spin fluctuations. So there is certainly a coupling between pneumaticity and spin fluctuations. And of course, if you have this magnetic transitions becoming, let's say, very unstable, if you enter close to the quantum critical point of the spin susceptibility, enhancement of spin susceptibility, you can also expect something going on in the pneumatic fluctuations. And that's what I think what's going on here. And of course, this means that we have a very interesting region here. So we have these very slow pneumatic fluctuations, which are coupled to the spins. And somehow this should also show up in unusual spin behavior. And that's also what we see. So what I've plotted here is also measured on these single crystals now, the NMR relaxation rate on compounds where you still have the magnetic order. You see the strong peak. And then this magnetic order disappears. And then you observe a very funny, very unusual behavior of 1 over T1T. That's plotted here for one of these underdoped compounds, which is hardly or not really superconducting. And that's just a comparison of a compound which still shows magnetic order. We have this strong enhancement, this strong peak, which you expect at the magnetic ordering. And then we have this very funny, very unusual behavior of 1 over T1T. And this is still present in the optimally doped compounds. So the compounds shows the highest TC. Also there we have this very unusual behavior of 1 over T1, telling you that at least this whole underdoped region is a very unusual material. So we have this very soft pneumatic fluctuations, very soft lattice, very soft orbital degree of freedom, and you have an extremely soft spin degree of freedom. And all of that is strongly coupled to electron transport. And therefore it's apparent that you have this extremely strong scattering of the electrons. And this of course explains you, at least qualitatively, that you are very close to localization. And only if you go to very high doping, these things disappear and things more and more become like usual metals. Okay, these similar things you can also observe in these fluorine doped compounds. This we did earlier already, that you also have this very funny relaxation with very funny, very unusual slow spin fluctuations. And I think now it's becoming clear that this is definitely connected also to these pneumatic fluctuations, which are very soft in these optimally doped compounds. And only if you go to overdoped compounds, you end up with something which looks more or less like a usual metal. Okay, that is the first part. Maybe I add a couple of transparencies on these thermoelectric properties, which give you even more information now that these systems are really very unusual metals. So what we are measuring now is we take again such a piezo stack. We take a sample, we measure we apply a temperature gradient, and we measure the thermal power and the Nernst effect. And both of that now as a function of a strain. And the strain which we can apply here is tiny, 0.08%, but it's still sufficient to see a signal. And that's shown here, just an example. So that's the way how we do these measurements. So we switch on a heater. The heater induces Seebeck, the thermal power. So you see a voltage. Then we switch on the piezo and you see a change of the Seebeck effect, switch off the piezo again and the heater. So that's then the strain dependence of the Seebeck effect. And that's here measured at a different temperature, and you see the Seebeck effect is negative and the strain effect is still positive. So you can really discriminate these two things. What we then do is measuring these effects, these small effects, as a function of strain plotted in this way from the slope. We get then the change of the Seebeck effect as a function of strain. And the same you can even do for the Nernst effect, which is even a little bit more complicated because now you have to apply also magnetic fields, negative and positive ones, and you have to subtract the things. But also here, you can easily follow the change of the Nernst effect as a function of the strain. That's by itself is already a real surprise because typically these effects are zero in usual metals, and now you can even measure their change as a function of these tiny strains. Seebeck effect, what do we measure here? So it's not scattering. So it's really a different quantity than the resistivity. What you measure here, if you, for example, take this easy mod formulas, what you measure here is the energy derivative of the conductivity. So energy derivatives of density and mobility. And it's of course well known that it's very, very sensitive to details of the Fermi surface. Seebeck effect. So and if you have the parent compound equal to 0, so you have basically undoped compounds, so holes and electrons with the same amount. Therefore, you have this crossing of the sign close to 0. If you electron dope the system, it becomes negative. So in both cases, we can then now follow the strain dependence of these things. And the first message is it does not change when you change the sign of the Seebeck effect. So that simply means that the strain derivative is independent on the sign of S. And this, the easiest way to explain this is that this really band selectivity of pneumatic fluctuations. So apparently only part of the Fermi surface, if you have these holes and electrons, really feels pneumatic fluctuations. Next thing is that in both cases, you can again fit these Curie-Weiss laws, and the Curie-Weiss constants which you obtain here are very similar to that what you get from the resistivity. However, these X dependence of the size of the effect is different. So the Seebeck effect here is much larger in the parent compound than it is in the dope compound. So in that sense, already telling you that it's not easy to take the same susceptibility. It's not straight to take the same susceptibility. And it's also maybe remarkable that when you do the same experiments on the barium 1 to 2, it's surprisingly similar. So that seems to be rather generic, this behavior, how this detail of the Fermi surface changes as a function of strain. Nernst effect is even more complicated in some sense, because in simple metals, the Nernst effect is always zero. And some of you might remember all the discussions on the cuprates on the reason of the Nernst effect, which I will not solve. So Nernst effect is the energy derivative of the Hall mobility. And here you see compounds, the parent compound and the dope compound, very much different in the ordered phases, but at high temperatures rather similar. And also for the Nernst effect, we can follow this change as a function of a strain, which is, for me, it was a real surprise. That really tells us that really details of this Fermi surface are extremely strongly dependent on details of the lattice. You can determine these susceptibilities if you want, a Nernst susceptibility, Curie-Weiss constants as you see it from the resistivity. That's easy. Again, finding for parent compound is larger than that for the dope compounds. And let me at least show you some first attempt how we can discuss these things. So when you write down the Seebeck effect, is take this mod formula. You can discriminate, or you can write it up in the following form. It's a product of so-called Peltier tensor times the resistivity. And here I assume a single band, so I forgot about all these complications due to multi-band effects. And if you do that, you can, and this may be relevant for this dope compound, you can determine a Seebeck susceptibility, which then is a sum of a susceptibility coming from this Peltier tensor. And this is something which is really measuring details of the Fermi surface usually, plus the second contribution, which comes from the resistivity here. And this is a susceptibility from the resistivity, which we know, which I have shown you earlier. And you can do this analysis, and then you find out that you definitely need two kinds of susceptibilities. You cannot take the resistivity values to explain the Seebeck effect. That's also already clear from the concentration dependence, and both of that have similar sign. So there's certainly a very strong change of the Fermi surface. It's quite natural to assume that this is really due to some orbital degrees of freedom, and that might be a starting point for let's say more calculations. What we did then is to take these susceptibilities, which we derived experimentally, to model the Nernst effect. This can do that along these lines, and details are described in this paper. And this is, again, without any assumption, without any fitting parameter, you can reproduce the Nernst data then from thermal power and resistivity and from their strain derivatives. That by itself is already a funny story, a very unusual thing, but telling us that this approach, having these two kind of susceptibilities, two kind of strain dependence, makes a lot of sense. Okay, that's what I wanted to tell you today. So I've presented you some, let's say, first results on these first series of single crystals. It's still work in progress. We try to get the fluorine doping working. We have now also systems with higher TC. I've shown you this kind of phase diagram. I've shown you this very prominent, very pronounced double peak feature, which you see here in the pneumatic susceptibility, somehow inferring that indeed pneumatic susceptibility is strongly coupled to superconductivity here, and it is coupled to spin fluctuations, which leads to very strange behavior in the normal state of these materials. And then at the end, I've shown you some first results on strain derivatives of more complex transport properties like Seebeck effect and Nernst effect. All of them strongly depends on lattice, very strongly shows that the pneumatic instability is very crucial for the electronic state here. And I think that also gives us, let's say, first new approaches to understand this coupling, which seems to be band selective, and which seems to be very strongly connected to the Fermi surface. So thank you very much for your attention. And if you want to learn more on that, there are papers on all these different things which I discussed today. In particular, this strain derivative of thermoelectric effect will appear soon in this Quantum Materials journal. The resistivity has been published last year in PRL. So thank you very much.
Thank you very much, Bernd. Yeah, any questions? Yeah, this is a very nice talk. Hey, Jan.
Hi, guys. How do
Hey,
you
how are
like?
you? Good to see you. Hey, Jan.
Yeah. It's not only to show my hair. I mean, you have a lockdown of barbershops, so I haven't been getting a haircut for the last 2 months. Next week, I'm up. Yeah, I haven't been paying too much attention to these iron superconductors for a while, but when I was listening to Bernd in the first half, I got kind of a very simple thought. Right, so you look at the pneumatic susceptibility, and it's basically associated with electron system, right? You look at the resistivity, and then you have this trouble that you look at the structural phase transition, right? That starts to broaden out. But it seems that the pneumatic susceptibility is still behaving in a pretty orderly manner, right? It's a nice QE wise, etc. Now, this may be an obvious thing, and I don't know whether everybody realizes it, but I would rationalize this as the electron system wants to do the pneumatic transition, right? So pneumatic proper, and when the pneumatic susceptibility gets large enough, the lattice couples in and promotes the transition to a first order, while by itself it would be like to be a second order, right? It's Curie-Weiss. And then when you have the first order transition and the lattice is coupled in, the lattice is talking in a very different way with this order than the electron system is doing. Right? The electrons are kind of self-annealing things. Right, so could it be that this sort of disconnect between the neat and orderly behavior of the pneumatic susceptibility contrasted with this very disorderly behavior of the orthorhombic transition is just about it, this sort of, turning into a first order transition when the lattice starts to feel the pneumatic susceptibility. And then when you have that, you can have this sort of Imry-Ma type of physics, right? The first order transition plus this order gives you puddling that is smearing out a transition. Could that be? Is this a thought that other people have had?
I don't know whether I really got your point correctly, but definitely I think there's something interesting and correct in there, because you have this extremely strong pneumatic susceptibility here at low temperatures. And why is there no long range order? What's really inhibiting this long range order here? And I think that could well be disorder, but not disorder in the sense of, let's say, some impurity atoms. I've shown you this in the beginning.
I'm saying something else, right? So there's this ongoing discussion forever whether this pneumaticity is driven by the lattice, right? So that you just have a silly structural transition, or is it like the electron system by itself wants to form a kind of quantum-liquid crystal or liquid crystal, and therefore you get this very strong pneumatic susceptibility that you see in the resistivity, which is an attitude of electrons, right? You really look at the size of the electron system. And they're kind of coupled always, right? So when there's a pneumatic susceptibility, which is purely electronic, starts to grow, at some point, there will be kind of a critical temperature where the lattice starts to communicate with it. And then, it's not very surprising to find that it turns into, as I remember it, a first order structural transition from tetragonal to orthorhombic. Having said that, when you have the lattice and there is disorder, right? You do expect that you get a sort of puddling, which is just silly, you know, having kind of orthorhombic domains that are messy in a detectable background, blah, 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 blah. Right, so where you could switch off the electrophonic coupling, it could be that you would have a very neat second order electronic pneumatic transition, but in fact obscured because you see it indirectly through the lattice, and the lattice feels a lot more about its disorder than the electron system is doing. The electrons are self-averaging, right? They're self-annealing, they're very quantum mechanical, they're way more liquid than atoms are, so to say. Could that be?
First of all, these systems do not show first order transition. So they're already second order in the parent compound. First order is, I think, in barium 1 to 2 in these compounds is second order. But I think they're, but I agree. Yeah, it's
first order. It's
second order. It's second order, at least if you believe our thermal expansion and thermodynamic properties. But nevertheless, you're right. I think it is basically an electronic instability, which we probe via these strain dependencies. Yes, yeah. It's electronic instability and also this surprising similarity. And I did not show you everything. I showed you only, let's say, the strain derivative of the Seebeck effect, which is identical for barium 1 to 2 and for these systems. You can have a look at the Nernst effect. It's identical. You have this completely different system, structurally completely different, a lot of different properties, scattering completely different. One is a nice metal, the other is a lousy metal close to localization. Nevertheless, these very sensitive probes of the Fermi surface, so thermal power typically measures if you have a peak in the density of states or something like that. These are basically identical in these systems, telling you that this instability itself and also somehow the strain derivative, which is somehow still a little bit of coupling to the lattice, is very, very similar. So I'm absolutely sure that at the end of the day, this is an instability of the electronic system. Of course, lattice picks it up. And then this thing of disorder, which you mentioned, I think that's very, very important, in particular to understand this funny phase diagram where we lose somehow our structural phase transition. Also, it becomes, so here it's fairly sharp, it's a very nice phase transition, and then you start to dope and it becomes broader and broader. In the same samples, the other transition is sharp and sharp, it becomes sharper and sharper. So it's not some sample property, it's something which is more intrinsic. And in some sense, the answer, I think one possible answer of that is given by this figure here, and that's the doping dependence, that as function of doping, we induce some additional sites here, we induce some kind of disorder in this system, and that's characteristic for these 1111 type compounds, but that's another talk. So yes, it's an electronic instability, yes, lattice picks it up, and the lattice, the long-range lattice order is much more sensitive to an intrinsic kind of disorder, which you have in there. And finally, we end up with an electronic instability only. You still see this very nice boost of the pneumatic susceptibility, but without a long-range order of the structure.
I should keep my mouth shut, but that's basically what I'm saying, right? That the lattice may be much more sensitive to the disorder than the electron system is. In this sense, you see.
And that's what we see here. Maybe you lose the structure phase transition, but you can still, if you measure the susceptibility, you still can follow the electronic response, which just hits this line.
So maybe
can I maybe continue along the same line, more or less? I also wanted to ask myself, hi Ben, as to all these iron-based superconductors, people always speak about pneumatic, but usually people have in mind completely different microscopic mechanism. It might be simply any structural type of transition, or it might be something connected with orbitals, or with Fermi surface, or maybe with biquadratic exchange, purely magnetically driven, and so on. And my question is actually from your data. Can you say something about anything, actually, about possible microscopic origin underlying all these phenomena?
Okay, probably. So if I would say, okay, already the fact that somehow this magnetism and the other transition changes in a different way. One disappears previously, the other later on. might indicate that it's not, let's say, the same instability which you see here, which drives the system to the spin density wave or to the magnetic state, and the other one drives this pneumatic instability. But of course, a lot of theoreticians will disagree. They say, okay, that's
fluctuations.
Which I don't know. So that's what I can say. What I can, maybe we have to go a little bit further in analysis of this thermotransport, because there it's not scattering. And I think typically when people discuss pneumatic susceptibility, usually they take this anisotropic scattering as a main mechanism. And I think what we see here is that there is indeed a very subtle response of the Fermi surface as a function of strain. And I think this, for me, looks more like orbitals. That's one story. Then the other story, which is also, let's say, maybe is something which is homework for theoreticians. So why is does this behavior here? So we have the sign change of the thermal power, but the pneumatic susceptibility shows the same sign. So it's really, let's say, orbital selective. It's really related to one part of the Fermi surface only. And this, again, could give us, let's say, at least when if we do some more realistic modeling of this, this could give us an idea how really the intrinsic mechanism of these things comes up. So
but at least it looks that it's not spin driven, yeah?
I would say that this looks more like orbital driven, yes.
So so let's quickly get two more questions. Chimiao and then Luca. Yeah.
Yeah, Bernd, so I had this question about 1111 versus 122. You know, as you mentioned at the beginning of the field, the evolution looked very different, and now you're telling us that maybe there's a more similarity than realized earlier, which is wonderful. I had two questions in this regard. So in nickel-doped 122, and I think in cobalt-doped 122 as well, there was some indication for glassy behavior in the near optimal doping at low temperatures that sort of interrupts the higher temperature quantum critical like behavior. And I wonder whether in this system you have the way to measure slow response or just dynamics in some way. That's question number one.
So let me first maybe first a short remark to the similarities and differences between 122 and 1111. So what remains is this remarkable difference in the normal state that we really have this system which is close to an insulating state. So if you look at the resistivity, it's really different. So the coupling is much stronger here. I don't think that this is really understood. What is definitely the case, we have a more two-dimensional systems. We have not this intermetallic behavior, not 3D systems. We have this oxygen in there. Maybe the lattice coupling is stronger. I don't know, but this remains. Now, if you already go to something like thermal power and Nernst effect, the similarity is unbelievable. Even such a quantity like the Nernst effect as a function of doping is basically identical, telling us that these details of the Fermi surface have to be very, very similar in these 1111 type compounds. Okay, that's maybe the point to point one. Coupling is somehow stronger, TC is higher, resistivity is much higher. Okay, maybe that's not so stupid, but that's what we learned. What the underlying electronic structure, details of it seem to be very, very similar in 122 and 1111 compounds. Okay, now the glassy behavior. Of course, we have the NMR, and for the NMR, this I did not push that a lot. So we have this. Okay, let me have where it was. Yeah. So you have these long range order things, but there on top there's of course some kind of short range order phenomena going on there. It's a little bit glassy, at least short range ordering. Let's call it like that, and that's. Maybe it's connected or is appearing close to these, let's say, quantum critical point for magnetism. On the other hand, you know, this is really challenging to get the crystals. And this, I think it's too early. For me, it's too early to say this is crystal or this is intrinsic. This I don't know. But there is, from the NMR, we have some, also, if you look in the paper, which is on the archive, you see there is a region in the phase diagram where we see some kind of short range phenomena going.
Is it commensurate or incommensurate?
Well, NMR probably doesn't know.
I have no idea. So at the moment we have these NMR data yet. So there's, as far as I know, for at least for our crystals, there's no neutron data yet.
Just to follow up, so in 122 again, one could maybe avoid this glassy-like behavior by looking at the phosphorus doping as opposed to be cobalt or nickel doping. And I was wondering whether, from materials perspective, whether one could also look at 1111 phosphorus doping.
Yes, of course. The big challenge is to get fluorine doping in there, because fluorine is out of plane doping. And just looking at resistivity, looking at the phase diagram, there's tremendous. So the TC in this cobalt, the maximum TC which you get in the cobalt doped samples is about 11 Kelvin. If you take the same samples with fluorine doping, you get 30 Kelvin. And these systems are much cleaner, but it's even more challenging to get these crystals. And we are working on that since years, I would say. And so far, we are not able to get, let's say, the phase diagram for the single crystals or fluorine doped crystals in a way that I can present it. Maybe I can do it next year, but at the moment, I'm not able to do it. Yes, there is a way. It's fluorine doping. It's out of plane doping, which should be, if crystals are nice, which should be really perfect in that sense.
Luca?
Just a comment, but that you are doping with fluorine or cobalt, you get the disappearance at the same doping. So
more or less.
So and the two.
You see, for fluorine doping, the phase, at least as far as we know, is more sharp. So this, and it is maybe slightly smaller concentrations. About 3%. For cobalt doping, it's 4%, but it's nearby. And now we are discussing real samples where 3% of fluorine doping and 4% of cobalt doping. That's okay. The precision of measurements. I think could be that for fluorine doping, it's slightly smaller. That doping is slightly more efficient, but the difference is pretty small.
Okay. So if no further question, let's thank Bernd again.
Okay. Thank you very much.
Yeah, thank you very much. Yeah. So next we're gonna have George Zawaski from UBC.
Yeah, if I can.
Can you Bernd? Can you stop sharing and get the George?
I try my very best. I don't know.
Well, you can just keep on going, Bernd. It's very interesting.
Yes, thank you, Bernd.
Okay, so now I have to somehow find my way.
So while George is getting his GPT get together, Bernd, so do you actually mean that in the cobalt doped 1111, you actually have a quantum critical point then? Are you suggesting the quantum critical point from pneumatic phase is driving superconductivity? Are you suggesting that, or is in just?
I showed you the raw data. So if you look at the Curie-Weiss temperatures of the energy scale, it hits zero exactly at optimal doping. So this looks like beautiful textbook quantum critical point behavior for the pneumatic susceptibility, and that's just found there where superconductivity shows the highest TC. And without any manipulation of data, it's just looking at the raw data you see there.
Okay, so you're suggesting the pneumatic phase plays an important role then? Yeah.
Not me, it's the data.
Okay, thank you. Okay, George, yeah, it's all yours.
Okay, thanks. Well, thank you very much for having me here. Let's see, I want to go to presentation mode if I can.
Oh, you're showing the presenter's mode. If you switch your display.
Oh, let's see.
It's in the middle bar. It's a display setting, and then go there, and then you can switch your display. I think you have two monitors.
I have two, yeah.
Yeah, just go to the display. And no, yeah, just go to on top of the cursor. The middle one, the left one is to show a text bar. Middle one is a display setting.
This one?
No, look on top.
On top. Oh, yeah, display setting. I see.
Yeah.
Yes, okay.
Yeah, swap. Yeah. Okay.
Okay. Okay. There we go.
Perfect.
Yeah.
Thank you.
Okay. Well, thank you very much. It's good to be here. And actually, maybe the end of my talk, if I ever get there, is going to be similar, or is going to create the same kind of issues, perhaps, as what Bernd showed. And but in the meantime, I simply wanted to talk a bit about the single layer iron selenide on STO. That's what we thought we were going to talk about initially, but I think the program has changed a little bit, but that doesn't really matter. So the single layer FESE is, iron selenide itself, of course, is also a superconductor. It doesn't have a magnetic transition. So we all feel that, hey, this is a nice thing to study. Transition temperature of bulk iron selenide is very low, about 8 degrees Kelvin, if I remember correctly. And it has a very, very low carrier density, a very low Fermi energy, and it has only a Fermi pockets, only electron pockets, and apparently no hole pockets in it in the single layer type material. Okay, and that all creates interesting questions again about magnetism, about the interaction of magnetism and the lattice, which is extremely strong, as we know already from Ole Gunnarsson's or Ole Anderson's work from way back when, just from density functional. And I'm going to show a little bit of that kind of stuff. So these are the people that were involved in this. Fengmiao Li done quite a bit of density functional theory together with Ilya Elfimov. Ke, you know, is a new professor at UBC, and he has done very nice work on single layer FESE on STO. Chung Liu, who has done some angular resolved photo emission also together with Ryan Day. Okay, so I'd like to talk a little bit about the replica bands and RPES and electron phonon interactions, then a bit about the atomic and electronic structure issues. Local iron fluctuating magnetic moments is another thing I want to talk about. And it'll be a different kind of fluctuation than we generally think of it as, for example, in the case of the cuprates, and charge transfer from the STO substrate to iron selenide. And I think I won't have time for the double layer iron selenide type work. Anyway, well, I should mention the double layer because this is one of the big problems, of course. You know, we all have problems with what actually the structure is, what actually the chemical composition is. Even in the case of iron selenide, one claims that from Kava's work, that the line phase, the real line phase is something like 1.01 iron selenium. Okay, so there's extra iron in there of a very typical, very small amount, which gets me to think about, you know, your very low concentrations of manganese, for example, that really affect the superconductivity and the behavior of your 111 crystals, which you, of course, have very nice crystals. The iron selenide on STO as a thin film or as a monolayer, of course, is even much more difficult. We actually don't know really, as far as I'm concerned, what the chemical composition is. We also don't really know what the structure is. But we know something about the electronic properties. And if you put iron selenide on STO and dope it with electrons, right, you get a transition temperature up to 65 Kelvin, at least from spectroscopy, and that's from tunneling or from photo emission, actually looking at the superconducting gap and so on. From transport, it's more like 40 Kelvin that you get. Okay, let me take this out of the way here. So you all know what the structure of iron selenide is. It's not polar, which is very nice because many of the other materials, as you know, are polar, and that always creates a bit of a problem for surfaces. So for photo emission, it's very, very nice to have a non-polar material. Now, of course, when you put it on strontium titanate, it may be polar. As a matter of fact, it probably is. But let's just go ahead with this first. So the photo emission results, so this is from Lee, Nature paper, ZX Shen's group in Stanford. And you see that there, you see at the gamma point, the left hand side here. I think oh, you can't see my cursor now.
We can see your cursor. Yes.
Yeah, you can see it. Okay.
Yeah, we can see it.
We see your pointer.
Yeah. Okay. So on the left-hand side, you see that there's a big gap. There's no whole pocket. It's far away from the Fermi energy, and in the middle there, you see the dispersion at around the M point, which shows. Actually, this is in the superconducting state, so you clearly see the bending off, you know, the Bugoliov type of quasi-particle type structure. So you see a superconducting gap there, and you see this this white stuff with the blue dashed line in there. That is basically the a replica band. It shows exactly the same kind of structure. Even the bending off is the same. And you even see the second replica a little bit. And that looks like an electron phonon coupling thing of some sort with phonons of the order of 100 millielectron volts, so 90 millielectron volts to 100 millielectron volts. Okay. And just going on quickly, this shows that again. And we see here, I've now drawn this blue line at the bottom of the superconducting M point, at the M point, and of the superconducting material. And you see that there is a clear gap between the bottom of that and the top of the whole band at what formerly was a whole band at the gamma point, oppositely dispersing. Okay. And that tells you that if this material, so this material has to be doped, because you cannot have, you know, a non-integer number of electrons just floating around without being compensated. It would have to be charged. It cannot be neutral, charge neutral, the whole material. Okay, so it has to be. So if we would take out those electrons, then this material in the rigid band-like sense would be a semiconductor and not a metal in the first place. So this material in the undoped phase, according to this, should be a metal. Now, I just want to talk about these replica bands, but I want to be very short because I want to get to the rest, which is more interesting. There's two ways of getting these replica bands. One way is that there is an electron phonon coupling of the d electrons, which are the electrons basically at the Fermi energy of iron, coupling with the phonons of strontium titanate. And it would have to couple with these Fuchs-Kluwer type phonons, and I'll describe them in a second. And that's those are at about 100 millielectron volts. They're the longitudinal optical phonons in the bulk that are actually the transverse optical phonon corresponding to that longitudinal optical phonon is your soft mode. It's at 10 millielectron volts or 15 millielectron volts. Okay, very important. But it could also be that the electron on its way out is actually exciting phonons. This is very common in photoemission results, where you can have plasmon satellites, for example, coming in as shake-off, people call them peaks, and they could be extrinsic or intrinsic, caused by either the fact that you have removed an electron from the iron and have a hole propagating there, or for the fact that the electron going out is actually exciting the phonons. And I just want to, so those are on the left-hand side here, that shows these two different types of things that could be happening. In photoemission, you have an electron coming out. Now, the reason why this is interesting is because there are high-resolution electron energy loss experiments done where you shoot an electron in on the same system, electron in, and scatter it more or less specularly, and look at what the energy loss is. And that energy loss spectrum is shown on the right-hand side under the H reals, okay? And you see that those peaks in the, so this is the zero loss line here. and the peaks that you have, there are low energy phonons, of course, but then you have a peak here at about 60 electron volts, and actually you can see this replica band here also. It's at about 60 milli-electron volts. Okay, and it lines up with this peak here. I think I show that here. Oh, I first went over to this one. So this peak here, this real big replica, lines up with this one here, and that one lines up with that one there, and they look very much like the spectrum that you get for electron energy loss spectroscopy. Okay, so the question then is, here's now a second order peak, which also was there actually in the electron energy loss. So how do you, so you can, the electron energy loss stuff is very well understood. It's from way back when in the 1970s, Fuchs Kluwer and so on, they did this work on surface phonons, which basically in this case are the longitudinal optical phonons of the bulk, which are shifted a bit at the surface. Okay, and you can get everything just from the infrared data. Just we have no adjustable parameters. Everything comes from the infrared data, where we have all of the phonon frequencies. And I'm going to talk specifically about this one. Here is the phonon frequency at 400 Kelvin. It's very highly dependent on temperature. This is a transverse optical phonon at 14 milli-electron volts, and it has quite a large width, and it has a huge Q. The Q basically is the static dielectric constant. Okay, that is the oscillator strength, the amplitude of the oscillation. If you go down to 15 Kelvin, that energy goes down to 1.4, it's overdamped, and the Q goes up to 20,000. However, there is no temperature dependence actually seen in these photoemission or in the intensity or in the electron energy loss spectrum. And that's because there's a rule that omega squared times Q is a constant. Okay, so we get rid of that first, okay? So this is the transverse optical phonon, and you know from the Lidane, Sachs, Teller relationship that the longitudinal optical phonon is the transverse one times the square root of epsilon naught divided by epsilon infinity. And the Fuchs Kluwer surface phonon frequency is just the same thing, except you add a 1 because it's a surface effect. The vacuum has a dielectric constant of 1, epsilon naught plus 1, and epsilon infinity plus 1. And you can work out this theory perfectly, and you get beautifully all of these phonons, transverse phonons, yield you a Fuchs Kluwer phonon that you see in electron energy loss spectroscopy. And this is a Q equals 0. It's a longitudinal optical phonon that is perpendicular to the surface, polarized perpendicular to the surface. So if I just look at a material and have an electron coming in at fairly high speed, coming in like this, then as it crosses its electric field, of course, in the perpendicular direction would be pointing in that direction, but there's a horizontal field, but it is oscillating, it is pointing, it is pulling that atom to the left here, and when it passes it, it'll pull it to the right. And that, because it's going fast, it averages out because the atom doesn't have time to move that quickly. Okay, that's seen here. The arrows change, right? There. If you now go to the end, way out here, all you have left then is that you've left behind a time-dependent perpendicular field, right? And that time-dependent perpendicular field is the one that excites that phonon. And that phonon, if you do a Fourier transform of that, it has that frequency component in it, and it will excite that phonon. It has a very strong coupling to it. Okay, so is it extrinsic or intrinsic? So many people have tried. There's been theory done, a very beautiful work done by Lee, and on this. And a recent paper, for example, they had also with Tom Devereaux, they had this picture of having an oscillating dipoles like this, and they did a quantum Monte Carlo type calculation, oscillating dipoles polarized in the Z direction here, in the vertical direction, and they calculated what a d electron in iron selenide by modeling it with a tight binding like model, what the d electron in iron selenide, how it would couple as it moves through the iron selenide. Now, obviously, well, pretty obviously, it doesn't couple actually for this Q equals 0 mode. The Q parallel is 0, but it starts coupling for a Q parallel in these oscillators, a Q parallel, which is finite, okay? However, you got to be careful with that. Oh, shoot, now I'm here. You have to be careful with that because the if you have a Q parallel, then this is not a longitudinal optical phonon anymore. It's a transverse optical phonon. And the energy of the bulk transverse optical phonon is at 15 or 10 millielectron volts. So in fact, although the transverse optical mode has a much lower energy, it has a gigantic Q, so it could couple very strongly. However, the in TC, oh shoot. However, in TC, here we are, in TC, that phonon frequency is the prefactor. And so I can't imagine that it could give you anything more than perhaps a 5 degree Kelvin change. We actually did what I call a poor man's electron phonon coupling calculation, just to see what happens if we move the oxygen atoms in this polar mode in the strontium titanate and look at what happens to the iron selenide band structure. And remember, the iron is about 4 angstroms away from the surface of STO. Okay, so so we then did 2 things. These are Elias calculations. We just moved the oxygens up and down relative to the titanium. And another way is to stagger then the up-down mode. I show here the up-down mode because that's the one that is expected to couple most. That, of course, is the transverse optical phonon, and because it's at the zone boundary, okay, with a large Q. And then you just look at the band structure, and you see absolutely nothing happening. So the iron d electrons really seem to be insensitive to what is happening so far away in the strontium titanate. Now, there is in our paper that we published about this, about the extrinsic energy loss, we also gave the smoking gun experiment as to how to determine what it was. And that's the photon energy dependence of the replica intensity. It should go like this if it's extrinsic. And many people have tried to measure this. It's very hard to do simply because of the very large background. If you look at this spectrum here on the right at the bottom, you have this very huge background here, and you don't know what the shape of it is inside here. So it's very difficult to say what the relative intensities of these peaks are. But there's a very recent experiment, and as I say, there's a lot of experiments, and they go all, I know ZX as a group, and Stanford and in Berkeley, they've tried very hard also. We have also, but we simply couldn't make much sense of it. But here's a paper that just recently came out by with Daryl Shalom, and so these are good people, and Kyle Shen and so on. These are very reliable results and very nice experimental results indeed. But again, you have this large background that these things are sitting on. This, and what they did is they used a kind of a spline method. So they just pinned the points in between the 2 peaks, the blue one and the red shaded one, pinned the background there and pinned it on the other side over here and a few other places, and did that all the way through, okay? Now, The problem with that is that there is another peak in between here. Yeah, there is another peak. That's a 60 millivolt peak. And if you change that spline background in that region just a little bit, in this region just a little bit, then the intensity of this one will immediately increase by a lot. This spline always has to be a bit lower than what the experimental data shows because of the overlapping tails of these states that you have, okay? So it really isn't correct to do this. However, they did it, and what they found then, if they do it this way, is that it's constant. And that's exactly what you would have expected for electron-phonon coupling, intrinsic electron-phonon coupling. Okay, so they let's just assume this is correct. I don't think it is, but we'll see. But what they then find is that that intensity ratio between these two, between the satellite and the main peak, that of course tells you something about the electron-phonon coupling, lambda. And if you put that, if you use that electron-phonon coupling to enhance the TC that already was there because of the electron doping, which is about 40 degrees Kelvin. So just from electron doping, the temperature goes up to 40 Kelvin. And you would get about a 15% increase, okay? So it would go to 46 or something like that, which means that it's very small. So I say that, well, okay, I don't really want to worry about this terribly much anymore, simply because it seems to be such a small effect that it really couldn't, even if it was there, it couldn't really affect the superconducting transition temperature much. So we're left with the problem from why. What's that due to, this large increase in the superconducting transition temperature? And then we come into a very big problem. An iron selenide monolayer on strontium titanate, as I just showed you, should be a semiconductor, okay, with a small gap. And the bands at gamma are all below the Fermi surface in the experiment, and at the M point are above the Fermi energy at the M point. And what you get in density functional theory is that those are degenerate. In fact, density functional theory has a big problem with all of these, okay? So this is done with iron selenide on strontium titanate, and then separated with the assumed lattice constant of strontium titanate. Okay, so what do we need to do to get an indirect gap in the undoped iron selenide? Well, it's a very difficult problem, actually. You can do all kinds of things, and it's very difficult to get a gap unless you go to magnetism. And we know from the work of Ole Krogh-Andersen that whether you have a magnetic moment on iron or not very strongly influences the selenium to iron plane distance. Okay, the distance that you generally get from density functional theory is much smaller than it is experimentally. But as soon as you put in magnetism, then that distance becomes much closer to the experimental distance that is measured. Okay, so magnetism is something that that has a very strong coupling to the lattice, and this sort of matches with what we just heard from Bard about the 1111 material and other iron pnictide-like systems. Okay, so let's go and have a look at this. So this shows you the density functional calculation just in an LSDA calculation. And it's relaxed. And if you do LSDA, you actually find, and this is G-type. This is not stripy. This is G-type. Now, for many of these things, as far as lattice constants versus magnetism is concerned, the magnetic order really doesn't matter so much. What matters is whether or not you have a local moment. And the reason is that if you have a local moment, you cannot have 2 electrons in every K state. This means that these anti-bonding iron D states, relative to the selenium, these anti-bonding iron D states, you have to occupy more and more anti-bonding, higher energy anti-bonding states. And as soon as you occupy higher energy anti-bonding states, right, then the distance will be the bond itself is becoming weaker, and the distances are going to become larger. And this is exactly what happens. We've done this study for the iron oxides, for iron halides, and every time, if you look at a low spin, high spin transition, you get the same kind of thing again. In, for example, lanthanum cobaltate. Okay, so this, whether you have a local momentum, right, matters much more than whether or not or how it is actually ordered. And that's what I want to show you. So this looks very, very strange. So this band structure is completely different now. There is still between there still is a hole pocket and an electron pocket, although at 0 it seems at the M point, it seems that the electron pocket has disappeared and you only have a hole pocket, okay? And you have this strange band, which is almost flat, crossing very close to the Fermi energy. And the magnetic moment is distributed all over the place. It's 1.7 Bohr magnetons. That's what you get if you look at the minimum distance or the minimized density functional distance of 3.7 angstroms for the lattice constant, 2 atoms per unit cell, 2 irons. Okay, and by the way, the iron selenide, the iron selenium, the distance of the selenium to the iron plane now is 1.45 angstroms, whereas in the non-magnetic case, it was 1.37. So this shows you exactly this effect of the elongation of that bond simply because you're occupying antibonding orbitals. And if you switch on a small u, 1 eV, it changes completely again. And if you switch on a u of 1.5 eV, it changes again completely, and you have a huge gap. You have a gap. Remember, your Fermi energy here is always put at the top of the valence band, okay? So in DFT, that's the usual way of doing it. So the gap here is almost 1 electron volt. Okay. And you have this very flat band right at the Fermi level. And it has a very strong z-squared character, not xy, not y, x, z, y, z, but z-squared. Again, the lattice constant now is very large. It's 4 angstroms. And when you stretch things out horizontally, the vertical distance will decrease also, okay? So the non-magnetic, if you had this kind of lattice constant, the selenium would be much closer to the iron plane in the non-magnetic material. But actually, the distance now is 1.42 angstroms, which is much larger than, for example, if you use a Poisson-like ratio to determine what that distance is, it would be more like 1.30 or 1.28 angstroms. Okay, so again, magnetism, larger magnetic moment gives you this very huge change in the selenium to iron plane distance. Okay, but this is very strange, and we don't. This need not be the right answer, by the way. That this is the right electronic structure of this material with this dz squared band here. There's many other examples where we know that if you have these kinds of magnetic moments, then things like multiplet theory becomes very important. And multiplet theory is something that you can't do in density functional theory. Okay, so it is a purely atomic thing. And multiplets could cross each other, as they do in the cuprates. They could cross each other relative to what you would get from a density functional calculation, simply because they are multi-Slater determinant states and not single Slater determinant states. Okay, so, but something like this is going to happen. But what that band, those bands exactly are, that we're not sure of actually. Okay, so we then were looking at also other things that might happen. For example, the top layer, the top selenium in this STEM data down at the bottom, but also from the very beautiful surface truncation rod experiments that Kazhu did, actually, that those they showed that the selenium actually is not symmetric. The iron is not symmetric between the two selenium layers. The layer at the bottom is a little bit closer to the iron than the layer at the top, the selenium at the top. Okay, so we tried that, but that doesn't really do much to the band structure actually, although it has a very interesting effect. It has the effect of, if you do the density functional and LSDA calculation, you then find that you, in this G-type, you find G-type antiferromagnetic order, so not stripy. That doesn't mean that it's not stripy, but the lowest energy is not stripy in this calculation. But you find that the two moments up and down are not equal. So now you have time reversal symmetry breaking. So be careful. You have now a dipole and time reversal symmetry breaking. I wonder if that really happens, but we don't really know. I'm going to skip this part because I'm running way out of time. I do want to mention this. So if the material is doped, then of course, you have taken electrons from STO because the STO had extra electrons in it at the bottom of the D band. Okay, so they're over here. The Fermi energy for STO would be up over here, and there is electrons in the conduction band, the iron D band of STO because of the niobium doping or oxygen vacancies. And those are actually, the work function there is actually lower than the work function in iron selenide. And that means, and that I show on the left-hand side here, that means that those electrons will flow as much as possible to the iron selenide. This means you get a dipole layer shown at the bottom here, the plus and the minus signs. Okay, so the STO is going to be positively charged, probably accumulated at the surface, and the iron selenide will have a negative charge. And when you do that, you have a kind of capacitor. They, of course, attract each other. And indeed, in density functional theory, you find that now the distance between the iron selenide and the STO gets smaller. But there will be an equilibrium where that all, where the amount of charge transfer simply is stabilized. And that turns out to be this magic number of 0.12, I think it is, per iron. Okay, I am going to skip most of this. I want to now talk about spin fluctuations. And I want to stress that there are two kinds of spin fluctuations. Is it the 0-point spin fluctuations, as you have in an ordinary antiferromagnet, as in perhaps the cuprates? So if you have a spin 1/2 system in 2 dimensions, antiferromagnetically coupled, then the nearest neighbor spin-spin correlation function is minus 0.33, right? But in icing, if you didn't have the quantum fluctuations, in icing, it would be minus 1/4, minus 0.25, okay? That is the kind of spin fluctuation where one spin flips up and the other one spins down. That is the kind of spin fluctuations that we generally think are important for the magnons, right? They are the magnons. They give you the magnon propagation, and they're the ones that we think are important in the cuprates for superconductivity. Whether that's true or not is also still up in the air. Or is it a quantum fluctuation of the magnitude of the local spin? Now that sounds a bit strange, but let me just show you what I mean. So if we have, we have here, we have an XZ orbital and a YZ orbital and a XY orbital on two neighboring irons. Shall we say the irons are in the X direction, okay, the neighbors. Then we have this kind of a picture. We start out with, and we put a magnetic moment on both of them, and we'll make them, put them antiferromagnetic, okay? And then look to see what happens. So I have the XZ, which is the black one, and the XY, which is the red one. And they both can hop to the neighbor, okay? So I hop, I then hop a neighboring spin here. I hop one of these spins to a neighboring XZ. No, that was the XY. Okay, this hops to the neighboring XY. By the way, an XY can't hop to an XZ, and an XZ can't hop to an XY. Okay, so the XY hops to the XY on the neighbor, and you get this picture up here, right? So now you have a spin of a half on each one of them. The energy cost is U plus J Hunt, putting the energy of this thing at 0. And the hopping integral is T. Then you can go ahead and you can hop this black electron from the XZ orbital to the left, giving it to the XZ on the left. Then you get this picture here. This is a spin 0 state, okay? And this here costs you twice Hund's rule to do this. And you have many of these possibilities. Yeah, you can go this way, but you can also flip spins around, making singlets or triplets. And so you have many, many possibilities, meaning that you have a lot of degrees of freedom with degenerate energies of hopping. You can also hop you can also have a spin on the YZ, hopping in the other direction, okay? Also with the XY orbital. So again, you have more possibilities of hopping back and forth. Plus all of the spin flip cases and equivalent paths and pairwise hopping in the perpendicular direction with YZ hopping. And if you see that the parameters are, you know, J is maybe about 2, maybe 1 or 2. Sorry, this should be U, I'm sorry. This should be U is about 1 or 2. The hopping integral is about 0.5 maybe. And the Hund's rule coupling, well, maybe it's 0.7, it could be 0.5. This is why Cotillard calls this a Hund's rule metal. It could be 0.7 or so. And you see that these, if you multiply this hopping integral here by the degeneracies that you have, right? Or by the square root of the degeneracies of what it can hop to, that's basically what you have to do. Then that easily multiplies this by at least a factor of 2 or 3, right? And then everything is of the same order of magnitude. So everything is mixed together very, very strongly, okay? And then you have basically a reduced magnetic moment on each atom. And the reduction of that magnetic moment is going to be extremely sensitive to the parameters. So that is the electron phonon coupling or electron lattice coupling that is all horribly sensitive to interatomic distances and to orbital ordering, of course. And this could even be result in orbital ordering, but of a complicated kind, yeah, of a orbital exchange type of process between atoms. I think this is something that Daniel had also mentioned, or maybe other people. So I think that these kind of things are really important fluctuations, also fluctuations which actually also can lead to pairing, okay? I think that's Kaliulin was one who described pairing in these kinds of fluctuations. Okay, conclusions? Well, I don't know. There are none, actually, except that I think that everything is important. And certainly magnetic lattice couplings are extremely important. I think these magnitude of the magnetic moment fluctuations are also extremely important. And maybe that's why we have these very strong dependencies on strain, on whatnot, when also in the band structure calculations. Thank you.
Very nice. Thank you, George. So before we have a question, so let me quickly announce, Chimio asked me to announce that next week we'll have a JP Pecoroni, also Peter Avenatti from Illinois, JP is from Maryland to give talks. So please attend. Yeah, okay. So first question, Bernd.
So I just want to comment on that because I like this picture very much, because it's not only orbital ordering, which you can explain this way, it's also the sensitivity to the external pressure.
Yes.
And that's something which is, let's say, iron selenium. Take iron selenium, you can, just applying pressure, you can go from whatever 8 Kelvin to 40 Kelvin. You can play the phase diagram with external pressure, and that's all very, very difficult. It's very much different from the cuprates. And I think this scenario where these high spin, low spin things plays a role is a natural way to explain that. And I like it very much. And then the other thing, the strains comes on top of that, orbital ordering comes on top of that. But that's, let's say, also a very interesting thing. Yeah.
Well, this could also result in orbital ordering, actually, in principle.
Yeah, of course. But this is a different channel. The other channel,
yes.
Even the easy one, the hydrostatic pressure should be large in this scenario, and that's pressure dependence, and that's actually what has been seen. I think it's also
well, that's what I found so interesting about your talk also, was this very, very large strain dependence that you have. Yeah.
Okay, more question?
Hey, George.
Hi.
This picture which you show now here with all this fluctuation, can it be really directly related to all this pneumatic stuff?
I think it can be, actually. I haven't worked through.
Did you try to do it, actually?
I haven't yet tried to do it. As a matter of fact, I wrote this picture this morning, but I had it in my mind already for a very long time. But this is the first time that I've actually shown it. It's not published or anything. But I really feel that because of these degeneracies, right, you're going to have a Jan-Teller problem. And I think that because of that, you're going to, it will want to do something. And it could, the one thing it could do is indeed orbitally order and give you the pneumatic type of phase. Also, as far as the lattice is concerned. And it could even do that before it does the magnetism, right? Because it's so strongly coupled to the lattice.
And this picture,
by the way, this would be an electron phonon coupling, where the phonons, where the coupling is in the Hopfing integral, not in the on-site energy.
Yeah, would it depend on the material, whether you are dealing with iron selenide or 122 or 1111, or it would be more or less the same in the whole class of this?
I think these things in themselves, well, these parameters, as I said, things are so sensitive to what these parameters are that I can imagine changes, but the qualitative physics, I think, would be the same. I think this would happen all over, but by changing parameters, you can either go into the pneumatic phases, or you could go into a magnetically ordered phase, or you could spin density wave phase, right? And maybe even a superconducting phase.
If I can only ask a very short question, experimental question, essentially. You say that superconductivity itself in iron selenide and STO is due to electron doping. But for that, you really need this STO, which is already kind of either oxygen depleted or with niobium or so on. So experimentally, does it really depend on the quality of STO? Because if you have very stoichiometric, very good STO, then you wouldn't get any superconductivity at all. Is it really what people
nobody actually knows because all of the STO materials. So the STO that is used, and that was this double layer I was talking about. STO when you, what they do in order to get rid of the oxygen vacancies as much as possible is they heat it up to around 900 degrees Kelvin and in oxygen. And that removes the oxygen vacancies. But what it also does is it removes some strontium from the first layer. And you then get an STO, which is basically almost pure, with a double layer of a double TiO2 layer. But it doesn't have the same structure as the terminating layer of STO, the TiO2 layer. It has a complicated structure. These are these beautiful results of this surface truncation rod experiments by Clejou and who was it? Anyway, you can look them up. I think it's reliable that they, and everybody really assumes now, and also the STEM data also shows you this double layer of STO. In other words, the subsurface strontium oxide layer is removed.
But if it's very difficult to make really stoichiometric STO,
yes, it's almost impossible.
Maybe one can experimentally do just the other way around, just to try to deliberately dope it by niobium and see whether
we are exactly
more favorable for superconductivity.
That's exactly the experiments that are being carried out right now at UBC, and those are experiments. You can do that in several different ways. But you're perfectly right. That's why, and there's a very interesting, I just saw it just this morning, paper in the archive about iron, monolayer of iron selenide on top of graphene. I think it's a double or a triple layer graphene, which is on top of silicon carbide. And there they claim, and they haven't done any photo emission. These are only small little islands of material, but they have done the what's it called? The interference scattering and scanning tunneling microscopy, okay? And from that, they could infer what the band structure really is. And they claim in that paper that actually that has a hole pocket and an electron pocket, but the width, the height of the pocket is only a few millivolts. So you have basically 0 electrons, but you also have a gap, which is a superconducting gap, they claim, which actually is comparable to the Fermi energy in that particular case, meaning, we're perhaps in trouble with BCS theory. But I don't know how reliable that is, especially the analysis of these scattering experiments, these backscattering experiments and the scanning tunneling experiment, how well you can actually predict the electronic structure to this kind of an accuracy, I think is very difficult.
Okay, thanks.
Okay, so the last question by Qimiao.
George, nice talk. So I just want to follow up on this picture that you're showing on the screen. There's some interesting systematics in the total spin spectral weight that's measured in the pnictides versus in the selenides. And I was wondering whether you have some thoughts.
You mean in the neutron scattering, or? In
the neutron scattering, integrate over Q, integrate over omega, you get something like somewhere around 3 or 4 Bohr magneton square per ion in the arsenides, and you get much more than that in the various selenides.
Yeah, well, I showed you pictures in LDA plus U with LSTA, where you actually have 3 Bohr magneton magnetic moments, depending, but then the lattice is also very stretched. It would automatically want to stretch, and the selenium would want to come down into the iron plane almost. Yeah, you'd almost get a rock salt like structure in the end. But these moments, we feel, are really quite large. So what we get is something close to 2 Bohr magnetons, which means a spin of 1, right?
No, but the question, I think, to me, it's interesting to at least look at the arsenides and ask question, what is reducing the integrated spectral weight? Of course, neutron doesn't see it, doesn't necessarily mean it's not there. So
that's right.
That's
no, that's right. It's difficult to say because you know, the form factors here are going to be very, very difficult, right? These are really complicated form factors in neutron scattering. So I really don't know how that would work out. Actually, with a model like this, we might be able to even look at what the form factor would do. That's actually rather an interesting question. Yeah.
Okay, so with that, I mean, let's thank George again. Thank you so much, George.
Thank
for
you.
giving a very nice talk.
Yeah. See ya.
Thanks to Ben
Okay.
as well.
Yeah, thank you. Yeah, thank you, everyone.
Hi, before this ends, I just wanted to say hello to George.
Hey, Jim, how are you
haven't
doing?
had
Hey, Jim Allen.
really fun to listen to a talk from you again. So in these weird times, it's just a nice chance to do that. It's good to see you.
Well, good to see you, Jim. Everything okay?
Yeah, we're doing fine. So
Great.
greetings to you and Marge from Kathy and me.
Okay, thank you.
All right.
Yeah.
Thank you.
Stay
Thank you.
safe.
Yep.
Great to see everybody. Bye.